Now we're going to kick things up a notch and ask, how can we describe a plane? And here it won't make sense to talk about that in the plane itself, since any plane in the 2 dimensions is just the entire thing. So we'll talk about describing a plane that lives in 3-dimensional space. And that's really our goal here. Here's our basic coordinate axes in 3-dimensional space, and it's really hard to draw a picture of a plane here. Just imagine we have a plane. This, of course, extends in all directions. Some plane that's sitting out in 3-dimensional space, you'll have to picture the extension in all directions. How in the world can we describe that? And the goal is to kind of take off from how we were describing a line. It's good to start with a single point that's on the plane, and we'll talk about that point in vector form. Say the point has coordinates x0, y0, z0. That's the coordinates of the point, and so I'm going to call this vector r0, where our vector r0 is just the vector from the origin to that point, x0, y0, y0. Let's see, fix this up a bit. Then z0. So that will be one point that's on the plane. But now here's where you'll have to use your mind a bit and visualize in 3-dimensional space all possible planes that contain this one point. Think of how you could rotate that plane in all different directions. How in the world would you specify among all the different ways to have a plane going through that one point, which one is the right one, the one that is this plane that we've drawn? There's not going to be one number that will be able to tell us the direction, but instead, here's the really nice trick. If you tell me a single direction vector, I don't want it to look, it should look exactly like that. Let me get rid of that. If you tell me a single direction vector, it kind of looks like this, which I'm going to call n, and you imagine that this plane is entirely perpendicular to n. We're going to call n the normal vector. Normal will mean for us perpendicular. It's used in math. The word normal is used in a whole bunch of different ways in mathematics. In geometry, we often talk about normal as being perpendicular. This normal vector will be perpendicular to the plane. It turns out if you have a point specified and you want a plane that's perpendicular to this normal vector, there'll only be one plane that actually meets those conditions. And our question will be how to describe it. So let's say our normal vector has coordinates a, b, c. How would we describe all the points on this plane? Well, there's a neat trick. I want to describe points on the plane. Let's say that's another point on the plane. I want to call this vector r, where r is the vector x, y, z. This will represent a point x, y, z that's on the plane. This vector r will be on the plane exactly when this vector that starts at the point x0, y0, z0, that's already on the plane. If you take the vector that connects that to the point x, y, z, that will have to be orthogonal here to the normal vector, because it will be a vector that lies entirely in the plane, so it has to be perpendicular to n. So our plane consists of all vectors r with the property that this vector here, and how do we describe that vector there? It's the vector that starts at r0 and ends at r. That's just the vector r minus r0, because remember, r0 plus that vector will get you r, so we want r minus r0, that's the vector in the plane, should be orthogonal to the vector n. Well, how do we say that two vectors are orthogonal. That's equivalent to saying the dot product of n and r minus r naught is 0. So the really nice way to describe a plane, if you know a point on the plane and you know a direction n, which is what we'll call a normal vector to the plane or a normal direction to the plane, will be that the dot product of n and any vector r minus r naught that lies entirely within the plane should be 0. So this is the description, n dot r minus r naught is 0. Remember, we're going to use in coordinates, n is the vector a, b, c. Here r is our vector representing any point x, y, z on the plane. And r naught was this particular point, x naught, y naught, z naught, which we know is on the plane. And then what does this equation look like? Well, this equation becomes a, b, c dot product with r minus r naught. That's the vector r minus r naught is x minus x naught, y minus y naught, and z minus z naught. And that should be 0. Well, what is this dot product? That's the first coordinate a times the first coordinate here. That's a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. So this is what we call, I've rewritten it here, the scalar equation for a plane. And you notice this is just a general linear equation for the plane. If I just expand this out, you could write ax, that's this, plus by, that's this part here, plus cz is equal to, here we have a minus ax naught, a minus by naught, and a minus cz naught. I'll just write that as d. Here d is your ax naught plus by naught plus cz naught. Anytime you have a single linear equation, that's one single linear equation in variables x, y, and z, the set of solutions in terms of points x, y, and z will be exactly a plane. Here a, b, c, and d are constants. So if you write down a single equation, for example, x plus 2y minus 3z equals 19, this will be the equation for a plane. Now what plane will it be? You just pick any numbers x, y, and z that make that true. That will give you a point on the plane. So you could pick, as one example, x could be 19. If x is 19, y and z could be 0, and that will be a point on the plane. If y, for example, is 19 halves, and x and z are both 0, that will also be a point on the plane. If z is negative 19 thirds, and x and y are 0, that will be another point on the plane. But you could pick all sorts of different points. You could pick z equals 1, y equals 1, this will then be negative 1, and x equals 20. In fact, of course, there's an infinite number of points on the plane, and you could just pick any x, y, and z that make this equation true, and you'll get different points on the plane. And you can get a picture of the plane just by drawing several points on the plane and thinking of the unique plane that goes through those points.